start. So homework updates, first thing. So two things. I realized as I was fixing the other class's homework that I had copied your totals into the wrong column and it didn't show up in the database correctly, so I've fixed that. So now finally everything for homework 2 should be correct. So when I set up your quizzes in Icon, the default is 1 point per question, and I forgot to change that when I set up your last quiz, and so that's why it says that you got 2 out of 4 points if you looked in there, and I changed it after the fact to be 2 points total, but they wouldn't let that propagate to your scores. So I don't use Icon really for anything other than just collecting your responses. I keep my own grading spreadsheet, and you can always tell, this is my dummy login, so I'm not doing very well in the course. But you can tell how many quiz points you have out of how many that we've given to make sure that you haven't missed one, as well as how many homework points. And so you can always check this. I try to update it the day after an assignment is due. If you think something is wrong or something hasn't been included, please let me know, but otherwise this is where I keep everything. So we're at midterms now, but you don't have a midterm in here. How much do you love me? Can I just say? Yeah, I've been hearing some horror stories about other folks that apparently midterms are not fun. I had no idea, but that's why I don't do them. My philosophy on this, did I tell you the first day why we don't do tests? No? Do you want to hear my philosophy? Yeah. Because in your professional lives from this point, there's never going to be a situation in which you have to dump your brain for 3 hours, and if you don't know it at that one moment in time, you're done. Big presentations, big things you're going to be prepared for in advance. You're going to know the questions. You're going to have something. You'll have notes to prepare. You'll be able to handle it. Plus, a better skill to practice now is your ability to take feedback and make it better. So, right, so have you submitted papers before, manuscripts for publication, a few of you? Did it get accepted on the first try? No, that is not a thing. That is actually not a thing. I know that's a pretend option, it's not a thing. The best case scenario is what we call revise and resubmit, where 3 people write and tell you all the things they hate about it, and also that it has promise. And you're supposed to take their feedback, apologize for being unclear, and write your response, right? So you're learning how to deal with feedback. Same thing if you write a grant, right? Grants hitting on the first try, also not a thing. But again, 3 reviewers give you some feedback, and hopefully you can make it better. This is the first time teaching this class. Did I get it right on the first try? Not a thing. But I'm hopeful that at the end of the semester you'll give me feedback, and I can take that feedback and make it better. So the idea of what I want you to do to practice with these things is continue to work with them and continue to develop. And hopefully the assessments are helping you understand when you've missed something, and you can go back and try and figure out why that is. So if you're ever sitting there and thinking, I don't know why these red answers are here, I couldn't figure out what I was doing, please let me help you. I'm more than happy to meet with you individually or during office hours, whatever is convenient for us. I'm also willing to do Zoom from off campus, so if we can set up meetings online if we can't find a time that we're both on campus, so that's fine with me too. So any questions about the homework that we are currently working on? Number 3. It is due next Wednesday, so you still have a ways. No one wants to ask questions, or no one has any? Terry has a question. Excellent.
So can you explain what residual variance is as a whole? Because I keep wanting to see something that says predicted actual minus predicted, and it's not and so then I get confused.
Yes, so what residual variance means depends on the model. Residual is the idea of E. So if you have, let me pull up an empty model here. Rewind, we'll do this slide real quick. This is lecture 5, slide 8. So in the empty model, there's no predictors. So E is how far off each observation is from the mean. That is literally the definition of variance. So at that point, even though it's considered mean square residual or residual variance, it's all the variance there is in Y to be had because you haven't explained any of it. After you put in predictors, residual variance always still refers to the variance of these E's, but conceptually it's variance left over. So it's the unexplained part. It's still the deviations around the regression line or around the means that you fit in your model. This terminology, by the way, will continue as you learn more about statistics. The same difference applies in the concept of a mean versus an intercept. So a mean of a variable is used to describe any variable that's not being predicted, whereas an intercept is the conditional mean that's conditional on the predictors being 0 after it's being predicted. So variance is to mean as residual variance is to intercept. Unconditional versus conditional.
Can you say that again?
Yes. So variance is to mean as residual variance is to intercept. The difference is unconditional versus conditional. So unconditional, like variance, how much variance is it? It's just variance. But to explain residual variance, I have to say it's variance remaining after ... It's conditional. Same thing with the mean. What's the mean of the variable? It just is. What's the intercept? Oh, it's the expected mean when ... That extra conditionality is what differentiates these terms. Does that help? Okay. And you do get the difference in the variance as part of your output, but it's given as a proportion reduction. And that was the part that we got into at the very end of class, the idea of R squared. So that is how it is given to you. But without fitting the empty model or looking at the descriptive statistics, you would never know where the original variance was. It just gives you what it is now and the proportion reduction relative to the original. Other questions? None right now? Okay. And just to remind you, if you get stuck, like if you get an error message and you're not sure why, it's totally okay to paste in your syntax and the error message into an email and ask for help. I can usually answer that pretty quickly, and then you can keep going. So you don't have to schedule an appointment with me. If there's an error to be made in syntax, I can guarantee I've made it before, and I can keep you from making it again. I have made every error that you could possibly make, I'm quite certain, and learned the hard way as to how to fix it. So, all right, well then we have some new stuff. I finally finished lecture 5, and I'm this close to finishing the second half of the example, so look for that later today. So we have some new stuff to talk about. And this is an example of me trying to push the envelope a little bit in terms of what is taught in introductory classes. What I'm going to cover today and next time is stuff that I wish people had known before they came to longitudinal analysis. So if you're going to plan to go there, guess what? You get a head start, courtesy of me teaching both classes. So we've got lecture 5 with multiple fixed effects for one predictor now complete. So I added after slide 21, as I told you. So we had gotten, I think we had gotten through about the intermediate summary here, and then you have extra stuff now starting on slide 21. But we haven't gone over the example yet, so I thought that that would be a good way to start so that we could actually look at the SAS code that generated all of these results and then go back over the concepts in the context of the numbers. So does that sound fine? Yeah. Better than hand calculating sums of squares, I'll tell you that. Am I right? It's like you can do it, but why would you? Kind of like people who make their own soap. I'm like, why is that a thing? It's one of the cheapest things you can buy, literally. I digress. So we got to example 5, part 1 here. So this is regression with a categorical predictor. In other words, do you remember what you would call this when you tell your advisor what you learned today? What is it called when you use a general linear model to predict a quantitative outcome from a categorical predictor? It starts with an A.
ANOVA.
ANOVA. What does ANOVA stand for?
Analysis of variance.
Yes! Analysis of variance. That's what we're doing up in here. All these fancy words. So you can trick people who don't understand how the models are connected by listing like your stats skills, and you'll be like, I know regression, I know t-test, I know ANOVA, I know this, and they don't know that it's just like one tiny tweak on the one thing. So you can totally work that to your advantage. So we are working with the same general social, what is it, GSS, social survey? People help me out, what is that called? Is that it?
Oh, that's what GSS stands for?
Yeah. I want to say general social survey, but I don't think that's quite right. It's something very close to that. But anyway, it's It's the data set that came with the Mitchell textbook, and it had lots of variables in it, and so that's why I'm playing with it, because then you guys can play with the data set at home as well. So I added a few things here after answering the same question from several of you. How to save your output. So once you work your way through all the models and you want to have a record of what you did that has everything you need and nothing else, I put that at the very beginning here. So in SAS, the command that I've given you to use is ODSRTF. That stands for Output Delivery System to a Rich Text File. So that is like something you can open up in a Word document. The first part of it, this ampersand file save, that refers to the abbreviation for where your folder is. In your homework, the variable that I call this is my file. So you need to change it or rename my file to be file save, one of the two. After that, you give it a name that is the file name. So that's whatever you'd like to name your file. Keep the extension as .rtf. You can style it however you like. There's a bunch of different styles. You can look it up if you want to have like more colorful output that comes in. Start page equals no is just an option that keeps it from opening up a new blank page every time you run something, which gets sort of annoying. So what happens is that if you invoke this command at the beginning, then you run all the stuff after it. So we'll run, we run, we run, we run, we do all this, and then at the very end of your program goes this, ODSRTF close. Once you run this, it realizes that you're done writing to that file and it opens it up for you to see. And it's been saved to the same place that your homework data was saved to as a record of what you've done. The analog to this in Stata, so you saw, I'll be at the bottom here, to close the file in Stata, it's log close. There's various options in Stata, but the one that I know works with earlier versions for sure is to develop a log file that's just a plain text file. So that's what I put you in for here. So log using, same concept except the extension is .log. And the way to refer to the abbreviation, instead of ampersand, it's a $sign. Just because each program had to do it just enough differently. So if you keep those things in your program, you'll be able to have a complete set of output that you can open anywhere using without having to be part of the virtual machine. Okay, now does that make sense? Okay, good. All right, so then we are doing some data manipulation to get ready to do our analysis. So when anyone hands me a data set and I'm supposed to do some sort of analysis for them, I would say 80% of the time is spent this part. Setting up the variables I need, making sure they're right, making sure there's not errors in them, you know, like no people that are 112 years old or something like that, because that happens, or no dead people who have scores. I've also seen that happen in some of the aging data sets. So paying close attention to how you're coding your variables and checking them, their distributions to make sure all of the values make sense. There's nothing more important than that, because if that hasn't done, then the rest of it doesn't make sense. So I'm going to be computing later on a new variable that is 3 versions of respondent class. This is the variable that we talked about in the lecture. So this part right here, before I do that, I'm creating what are known as value labels. So in SAS, it's proc format, and this name right here, F class, that is the name that holds the collection of 2 is this, 3 is that, 4 is this. So it is a name of a coding scheme. So I'm defining it so that if a variable has a value 2, it means this. If it's 3, it means this, and so on. And so once you apply these labels, rather than getting 2, 3, 4 in your output, you get the words. And so you don't have to remember off the top of your head what 2, 3, and 4 mean. So that can be helpful for categorical variables. So in the data set then, this is, I want to point out what I'm doing here. So data and set work together, right? Data means make me a new data set. I'm asking it to go in the work library, dot, and the name of the new data set, GSS. So it's a SAS data set. So if I only had just that section right there, it would make me a blank new data set named GSS in the work library. Instead, I'm saying set, meaning from, take it from this one and put it in my new one, and the one that it's coming from is work.gss full. So full is what I named the full Stata file that has all the cases and all the variables. What I'm going to do here is make some new variables, subset it to have people that are complete on the variables, and rename it as a separate file. That way, if I need to go back to the original, it's still there in memory and I can refer to it. So it's like save as a new name. Kind of like, final dissertation 3, right? Any of you have files like that? Final dissertation 4. Final dissertation. Yeah. So yeah, same principle.
So is this what we would do when you showed us like the dummy coding, and then it was like low and mid means, and then mid and low? Like, so this is what we would do to make that.
To make the variable is going to be right here.
But we do all these things first.
Well, I could have written them in any order.
Okay.
But yeah, so this step up here is just a separate thing that is creating a labeling system that we're then going to apply to that new variable. So I'm doing a bunch of things to make my life easier and to trim the data down into something that would make a good example. So I'm rescaling income into thousands. That's just so that we have smaller numbers to work with. It's easier to report, easier to talk about. I arbitrarily decided to dump some people out of my analysis because the outcome variable got really unwieldy, and I wanted you to have a nice, well-working example. So this isn't to say that in your data you should dump people like arbitrarily. That's not the practice I'm modeling here. But if you decide for whatever reason to legitimately select a subsample, right? I only want to study people who make less than 200,000 a year, for instance. This is how you would do it. So if this income variable is greater than 200, which means 1,000 in the new version, then delete. Means drops them out of the data file. Otherwise, they are kept implicitly. Likewise, I was going to study the relationship between income and age, and there were a few really, really old people, but not very many, so I decided to limit the analysis to people 75 or under. So if age is greater than 75, then delete for that reason. And then last but not least here, there was a variable called class, and it had 4 categories where they differentiated low class and working class, and not very many people selected working class. So I decided to combine them for the sake of the analysis, because to me those are somewhat similar. Again, not things you should do arbitrarily, just stuff. This is just sort of examples of data manipulation to help you. And so if class was 1, then the new variable class 3 is 2. Otherwise, the new variable class 3 is old. So I'm saying if the old one is 1, then the new one is 2. Otherwise, the new one is what the old one was. So I'm recoding only in one situation. Otherwise, I'm just copying the values over. I don't like that face.
No, it's fine.
It's fine?
Yeah.
Okay. Tell me if it's not fine. I'm not going to make you do like all this extra stuff, by the way. This is sort of like getting you used to seeing code and doing things. I don't expect you to memorize it either. Whenever I need to do this, I usually grab something I've done ahead of time that I know will look like this and modify it. Okay, what we do need to do, though, and you will get a chance to practice this in your next homework, I guarantee, is create the dummy code contrasts. So dummy code just refers to any variable that is a 0 versus a 1, and usually we make a set of them so that we can tell groups apart. So here, my original class variable now has 3 categories, 2, 3, and 4. For each of those groups, I'm going to selectively give a value to my new dummy code. So class equals 2 is the low working class, class equals 3 is the middle class, and class equals 4 is upper. I know that from the data set. So I'm saying if you're in class 2, then I'm going to make 2 new variables. And this is what we looked at in the slides. L versus M is a contrast that's going to distinguish the low class from the middle class. So it's going to be set to 0, semicolon, because it's a new variable. Low versus U, L versus U is low versus upper, also set to 0, semicolon, end. So this do and end go together. Like end is telling it, okay, I'm done now. Like do all these things, end. And then it goes to the next statement. So if it's middle class, then this variable here, L versus M, picks up a 1. So it's the effect of being in the middle class relative to low. And if class is 4 for high, then low versus upper picks up a 1 here to be the effect of upper relative to low. So why are we doing this? Because any model for a 3-category predictor means that you want to recover 3 different means. One of them is going to be given by the intercept. The other 2 are going to be linear combinations of the intercept plus some slopes. So in this coding system, the reason that I know what these variables mean is because of sorcery. I like that word. I made it that way. So the intercept we know is what? What's the definition of intercept again? Expected. Expected what? Can't quite hear you.
Intercept.
Intercept.
It's the outcome when x is 0.
Yes, it's the expected outcome when x is 0. So that's why I set each of these variables equal to 0 when class equals 2 is because what I'm saying is, all right, I want my low group to be the intercept. So I set up the predictors so that low would be the only group in which both of these things are 0. When I add low versus middle, that is now going to carry the difference between low versus middle, and low versus upper is going to carry the difference between low versus upper. So these are slopes, slope predictors that I'm creating here. They're binary, but as long as I have 2, along with the intercept, 1 intercept plus 2 slopes will perfectly reproduce my 3 means. And how many would I need if I had 4 categories? How many? 3 slopes and an intercept, right? And if I had 5 categories? 4 and an intercept, yep. Now, you can set up those 4 however you want. There are various strategies that give you things that are more or less convenient, but this is a simple one that's used probably most of the time. I shouldn't say simple. Relative to the other alternatives, it is. Let's put it that way. Okay, Danae, you don't look very happy. You okay? Okay. Oh, so your brain is all fried. I'm so sorry. Well, thanks for coming. I appreciate it. Now, I remember after I took the GRE, I skipped my afternoon classes that day. I was like, I'm out. I'm empty. All my cognitive reserve was just spent on this crappy test. So, all right. Last piece here, this format statement. This is telling SAS, hey, you know that new variable we just made, class 3? Can you put this labeling system on it that we made up above, F class? So that way when it says a 2 in my output, it'll print low class, and when it says a 3, it'll print middle class. Cool, thanks. Semicolon. And last but not least, I am selecting the data set to be complete with respect to all of the predictors that are eventually going to be in this example so that we're working with the same sample throughout. So this is an example of a function. Where is literally English. NMIS stands for number missing. The variables that go inside a function are known as arguments. In this case, this is a function that returns the number of missing values across the variables that we give it as its arguments. So I'm saying where number missing is 0, meaning I only want these people in my new data set if the number missing is 0. So it's an indirect way of saying kick them out if they're incomplete. Save them if they're complete. Where not missing, number missing is 0, means complete. Okay. Questions on any of the code for that? All right, stated code looks similar, although there's a few differences. Yeah, question?
I actually do have a question about
Sure.
these variables things. So logistically, is it, so if they skip, let's say it's a survey and they skip a question, and you're saying, I only want full data pictures. So like if they skipped a question about whatever, income, then you don't want to include them.
They will get kicked out of the model anyway at that point. a row of data has to be complete with respect to all predictors and outcomes to be included. So they'll kick them out anyway. So I'm just beating them to the punch so that my sample size doesn't change across models. If you have a bigger problem with missing data, then kicking people out is not the answer, and you'd want to do something that you'd have to learn about in another class. But yeah, there are more, I don't want to say sophisticated, but there's things people have developed to deal with missing data, but they take a lot more effort to implement.
Okay.
So that we'll say, not. Okay. So Stata code, a few differences. Gen, you have to stick in front when you make a new variable. Otherwise, it's new variable equals old variable. Label turns into label variable. Drop if is the same as if then delete. The recode looks a little bit different because it wants you to generate the new variable and then replace it conditionally. And so this is what the same dummy coding looks like. I don't know how to do group commands of if, then, do in Stata, so I wrote each one out separately, and so I did the code a little bit shorter just to have fewer lines of code, but it accomplishes the same thing. So replace the new variable if the old variable is equal to certain values. And you can also use greater than or equal, less than or equal, or those kinds of things. Stata allows you to define your label, your value label system, and then apply it right away. So it's label define. And then last but not least, I created a new variable that holds the number of missing values across the row, and then drop if the number missing is greater than 0. So it's analogous in idea, just a different set of words. All right. So all of that just to get a subset of data to work with and make one new variable that we're going to play with, which is categorical class. Are you ready? Yeah. Okay. So first stop, the things you already know how to do. So this should be nice and comforting, right? Like figure out the frequency. A lot of you did this in Excel without even having to get SAS, so you know how to do it in multiple programs. No worries on that. So right away I want to point out the difference in sample size across the classes. So we saw this in the PowerPoint slides, but the class that has a 20 here, the upper class, anything related to them is not going to be estimated as precisely as the other classes. This would also be where I check to make sure that the recode functions that I wrote are indeed correct, and I don't have like a value of 1 here or a 5 or something else that I don't know what's going on. Since personal income is a new variable, I went ahead and ran descriptives on it. So I'm doing proc means. And because I wanted to add variance to the list, I wrote out everything else that would normally be there. So n, mean, standard deviation, min, and max are defaults, but you have to write them if you add anything to the list. I want variance. Same thing in Stata. If you add detail, that adds extra stuff, including variance, and so that's the way to get that. And so here are descriptives for the variable. So mean 17, we're going to see that again come back as the fixed intercept from the empty model. 190, that's all the variance there is. That's going to show up as residual variance from the empty model. And how are standard deviation and variance related again? Square what?
Square standard deviation to get variance?
Yes, so 13 squared is the 190. So that's why it doesn't print both of them by default, because it's redundant. It gives you standard deviation by default, but I wanted variance so that you could see where this number is going to show up again as we start modeling. Okay. So here's the distribution of income. I made a histogram, bounded it into intervals of 5. How would you describe the shape of this distribution? Skewed. Which way? Yeah, it's up there. You can always read from the slide, yeah. Positively skewed. So there's fewer values on the right side because you can't have negative income, as it turns out. So there's a boundary here. Now, what are we going to need to be able to believe about the distribution of this to use it in a general linear model? What kind of distribution is the basis of the general linear model? Normal. So should I fix this? Should I transform it or, otherwise make it more normal? No, that's right, Terry. Why not?
Because you want to look at the residuals to see if they're normally distributed.
That's right. It's the variance that's left that we care about. It's the residuals after we're done predicting. If we're able to figure out why some people have these higher incomes, their residuals will move in and everything will look okay. So just keep in mind that the shape of it may dictate what kinds of relationships that you need necessarily with your variables, but just because it doesn't look normal doesn't mean that it won't work for the general linear model. So here's our empty model. You have plenty of practice doing this in your current homework, right? So empty meaning no predictors, so there's my outcome. So we have 190 as the mean square error, so that's residual variance, which right now is all the variance. And the fixed intercept beta 0 down here, that's the 17, that's your mean. That is also, by the way, given as part of your output for any model right here, for reasons that I don't know why.
What's it the mean of?
The mean of personal income. That is the outcome variable we're going to predict today. The rest of this stuff we're going to ignore for now. Other than this thing right here. What does that number mean? Well, step one, we can read the label above it, right? Standard error. Standard error of what? In the mean in this case, yeah. Because the intercept is not yet conditional on anything, it's the mean. So as a review, what does standard error of the mean tell you? Average distance of the sample mean from the population mean. Very good. As opposed to this number right here, that is standard deviation. 13.79, 13.79. So what's the difference? Homework question.
The difference between the standard deviation and the standard error?
Yep. That's what I want to know. Yep. What's the difference between these two numbers? So we did this one. Standard error of the intercept, or the mean in this case. That is the average deviation of the sample mean from the population mean. That sounds a lot like the definition of standard deviation, but not quite. So what's standard deviation?
The square root of the variance.
Correct, but not where I was going. I heard someone start talking. Yeah, it's the average distance of an observation in your sample from the sample mean. So standard deviation describes your sample specifically. Standard error describes how your sample supposedly relates to the population. Yeah, that's like the cans. So standard deviation is how far off each can is from the sample mean. Standard error is how far off the 12-pack mean is from the population. Going back to that example. Cheers. All right, now we get our predictor. And so this is repeated from the slides so we can revisit the logic of this. So how you set up your predictor variables then dictates what they mean. So this is entirely user determined. And I mean user not in a, like oh, he's such a user, but like in a good way, like the software user. The analyst, as it were. So my naming convention when I set up binary predictors as dummy codes is to put the thing that's the 0 versus the thing that's the 1. That's just my naming convention. So I'm saying this is L versus M because low is 0 and middle class is 1. Likewise, L is 0 and U is 1 here. So income is the original outcome variable to be predicted. It is predicted from this linear combination of fixed effects. And then E is what? Residual. It's the difference between the income that is predicted based on your class and your real one. And so an abbreviation for this linear combination of fixed effects here, what the model predicts your outcome to be, is our friend y hat. So you will see that show up in formulas and things to make it easier to describe what's going on. So I have written out how the model tells you all 6 of the things you might want to know. 3 means, 3 possible mean differences. The first fixed effect, the intercept, that is going to give you the mean for the low group. And that's because if you work out the prediction for how the model says income should be predicted for the low group, it starts out with the fixed intercept. The low group is coded 0 for this dummy code. It's also coded 0 for this dummy code, and therefore beta 1 and beta 2 cancel. They go away, and you're left with just beta 0. So this reinforces the idea that the intercept is the expected outcome when all predictors equal 0, because that's a situation in which they all 0 out and you're left with just beta 0. Doing the same thing for the middle group. Now we pick up beta 0 plus a 1, so we need the coefficient for beta 1. The beta 0 or beta 2 effect goes away, so we're left with a linear combination. Likewise, predicted value for the H, that should be U. Went with high. Beta 0, not beta 1 this time, does pick up beta 2. We're left with a linear combination. And then the 3 differences, 2 of them are given directly by the model. Beta 1 is the difference of low and medium. Beta 2 is the difference of low and upper. So there's one more that you have to ask for. Mid versus upper, the non-reference group. And that's a linear combination of the differences relative to the reference group. Now the code to do all this. I've written out all 6 lines that generate these 6 things. Only 3 of them are technically necessary, but I did so to be complete so you could see what's going on. So when you see these words referring to intercept or the name of the variable, they are referring to the betas that go with them, the fixed effects. So when I say intercept 1, what I'm saying is, yeah, I'd like to order 1 beta 0, like you're at the drive-thru. You know, I'm always stuck behind someone who has never considered before what they are there to order. It's like, yeah, it's like, no, get that in your head. We're all waiting. I need like 1. Wait, what? Okay, I need 1 beta 0 plus, like, would you like fries with that? No, thank you. Would you like to upsize to get to a giant Dr. Pepper? No, thank you. Okay, your order is beta 0, drive through. And that's the first line. The second line, I need 1 beta 0. I'd like to add fries to that. Drive through. Do you want a drink? No, thank you. Next one, I'd like 1 beta 0, no fries, but I want a drink. So it's just it's putting the 0s and 1, just filling in the values for what the predictor would be when you coded it originally. So whenever you have intercept in here, what you're getting is some sort of predicted y, because predicted y uses all the fixed effects in the model, all the variables that have predictive effects. The next three are different. The next three do not involve the intercept because they are differences between groups. So the first two statements here are redundant with what's in the model. Low versus mid is beta 1. So that's all I need. Likewise, low versus upper is beta 2. So that's all I need. It's the third one that we have to ask for extra. The third one works out to be beta 2 minus beta 1. Because you take the mean for the upper group minus the mean for the middle group, the betas cancel and you're left with beta 2 minus beta 1. And to keep them in the same order as everything else, I just put the minus sign next to beta 1 and the plus sign next to beta 2. Okay. And stated code looks very similar except for the const instead of intercept and the explicit multiplication by those coefficients and adding them together. How are we doing? Now, can I give you a brief aside? Have you heard of alpha inflation? Family type 1 error rate? Okay, I'm here to tell you I just don't care. And I'll tell you why. Because conventional wisdom says that in these sorts of situations where you want to go and look at extra group differences besides the ones that the model implies, that you have to worry about that you're p-hacking and looking at too many things. And I don't see any reason why these two differences that are given by the model are any different than a linear combination of them in terms of susceptibility to type 1 error. I just don't. So yeah, I'm doing 3 tests. For every 20 tests I do, if I keep my alpha at 0.05, one of them is significant as a fluke. I don't care if they're tests that are given automatically or things that are extra. I just don't make that distinction. Because if I recoded my variables to set the reference group to be something else, then those tests would be part of the model and I'd be asking for different ones after the fact. So you may have people who want you to correct for that, and that's fine. You can always add options to these commands to do so. I'm just not going to. Just not. So that's my my point of view. Ready to see some output? Why not? So let's look at the coefficients, the betas first, and then we'll return to sort of the model part up here. So I rearranged the 2 tables because they put the linear combinations first, which makes no sense. But this is the part that you asked for as the model. So that's what shows up just by doing model equals here, or in Stata, just this first line. So if you didn't type anything extra, you would get your 3 parameter estimates right here. Okay. So previously, my fixed intercept was 17, I think. Now it's 13. Strange or expected? Expected. Why? What does this mean now? Previously, it was the mean for everybody because we had no predictors. Now what is it?
Went down.
Went down. Because what does it mean now? Intercept is for the low group. Yeah. So the mean for the class equals low, the people who rated themselves as low class, whatever that means, their average is $13.6 thousand. The t-value that you get from taking this 13 estimate and dividing by the standard error is 21, which is not 0, but that's not terribly interesting because all that says is that people who rated themselves as low class make some money. So 13 is not 0. It may feel like 0 or thereabouts, but it's not according to this. So then L versus M. Is that a mean or mean difference? Mean difference, yes. And how about L versus U? Mean or mean difference? Heck yes. So-
quick clarifying, when you are looking at L versus U, that is not any relation to L versus M, right? So it's not like I'm adding M and U together to get,
Correct.
so it's separate.
Separate.
Okay.
Yep. So it's like low is your reference point, and you're going low versus medium and low versus upper. Yep. So L versus M, it's positive effect, which means income is higher for the group that's coded 1. The M's are the ones here. So predicted income for the mid group is predicted to be significantly higher by about $9,000 relative to the low group. So note that the word upper was not anywhere in that sentence. This is just mid versus low. Now, is 8,000 a lot? I'd like 8,000 more dollars. I'd be okay with that. Now, is there anything here that tells us, that can help us quantify, is 8 a lot? Is 8 0?
No, it's significant.
Yeah, that's our p-value here. So 8 divided by 1 gives us our t. Denominator degrees of freedom for everything in this table are right here, 731. P less than 0.0001. So yes, 8 is not 0. But we still don't have a good sense of, like, I mean, it's $8,000, but we don't have an effect size yet. This is an unstandardized coefficient. We can tell you if it's different than 0. We can give it a confidence interval for its expected value across samples, but we don't have an effect size yet. Same idea, different comparison here. L versus U. The 1 group, which is the U's, are 10,000 higher than the low group. 10 divided by 3 is 3 and some change, so that's significant as well. So far we know 1 mean and 2 mean differences. The others are all linear combinations of those. So if we take, let's see, this 13, the intercept, is the mean for low, so that line matches completely because it's redundant. Now I said I wrote it for pedagogical purposes, but in practice, when I do analyses, I will write all the groups out because that is like your trail of breadcrumbs, right? Like if you're doing analyses for your advisor and you want to send them output, you can't send them this top table because only you know what L versus M means, right? But you can send them the bottom table. So even though some of the things are redundant, it can be helpful to write it out what it means as part of your record. And so I do that on a regular basis. So if I take the intercept and I add to it the difference from getting from low to middle, that gets me to where middle is. 22,000, also not 0. Likewise, if I take the intercept for low of 13 and I add to it the difference for U, that gets me to my upper mean of 24. Also not 0. So if you're describing this analysis, like you could make a lovely little bar chart of your predicted means for each group with this information, you would give them each error bars that describe either plus or minus 1 standard error or 2 standard errors, your choice. But note the difference here. The last one is estimated a lot less precisely. There's only 20 people in it. So that's why the error bars would be important to convey. So now that we have the 3 means here, we can more easily track the mean differences. The difference between 13 and 22 is 8. That's beta 1. The difference between 13 and 24 is 10. That's beta 2. And the difference between 24 and 22 is 2. And that's beta 2 minus beta 1. How are we doing?
This should be upper versus middle difference.
Thank you.
When we are calculating the middle versus upper, we can also use the difference between the low to upper minus the low versus middle.
Yes. Yeah, this one, if you coded it the other way, then you would get the same significance level and standard error, but the coefficient would be backwards.
You mean it would be minus 2?
Yes, it'd be -2 instead. So yeah, the way that I do it is I always set it up so that the first one before the versus is the reference, and then relative to that, the difference applies to get from this to this. So it's 22 versus 21, or 22 versus 24 is 2. Did I fix the code? Yeah, that one's wrong too. Mid versus up. Thank you. I'll fix these and repost it. Thanks for catching my typos. I think I got it right everywhere else, but yeah. All right.
Would you go back to the other?
Yeah. This one?
Yep.
Okay. Yep. I labeled this wrong. It was a copy paste error. My bad. So mid versus upper is the third one. Beta 2 minus beta 1, or it's written here as -1 times beta 1 plus 1 times beta 2. Yeah, I got it right everywhere else. Okay. And since we're in this section here, residual plot. Look at that. Isn't that bad? Normal-ish. So residuals are okay. They also gave us the predicted residuals for each group, so we could look at the spread within groups. Looks relatively even across groups, perhaps a little bit less variance in the low group just because they're truncated at 0. But on the whole, I would feel reasonably okay about this. There are formal ways to test whether or not you have equal variance across your groups in the residuals. I was hoping to get to that this semester, but I don't think I'm going to. I think that's going to have to be a next semester topic. Okay. So now the rest of this. So this is how one would answer a question as to whether or not a nominal variable and a quantitative variable have a relationship. You need more than one fixed effect. You need as many fixed slopes as categories -1. But we don't have an overall sense yet of whether group matters, like putting these things together, right? We can talk about each separate contrasts, but we don't have an overall picture of the strength of the relationship between group, class in this case, and income. That's what this first part is trying to give you. So I found, in the lecture slides, I think I found one typo. So I wanted to make sure that I corrected that in this table. This is page 6, slide 16. That's not what I want. There we go. This is slide 16 in lecture 5. And so it's this right here. Oh, -1. I forgot that part. The reason for it is because I was deciding between two different ways of presenting it, and I decided to go with the one that is more common. And so I fixed half the table, not the other half in my initial things.
Oh, so that's the fixed one.
This is the fixed
Oh,
one.
okay.
Should be -1. Yeah. If it depends on how long ago you printed it or downloaded it. Like, then you got the fixed one already. Yeah, because I always post it right after I do something with it. So we talked about this. Yeah, this one here. Do you remember this? Mean squares, sum squares? Do you want to go over it again? Always, yeah. All right, so we'll back up here. So we want to answer the question more generally. Is there a relationship between this 3-category variable and our outcome? We've answered it in sort of more nuanced ways of whether there's group differences in each pair of means, but if we want sort of an overall level of prediction, the way you can think about that is to what extent does the y that's predicted by this model, the fixed intercept and the two fixed slopes, correlate with the actual y? So previously, we didn't worry about this when we only had one fixed slope, because if the correlation is significant, we know the predicted y correlates with the actual y. That's it. But now we have an extra step that we have to take to try and put this together. And this is the idea of a multivariate wald test. It's testing more than one fixed slope simultaneously, whether the set of them is different than 0. And so this requires considering two things: sums of squares, which is something analogous to information. It's the numerator of variance. So down here, for instance, this is sums of squares total. It's the difference between each outcome and the sample mean squared. So this is just original variance, this formula. Sums of squares total is the top part, the numerator. We also need to know how many fixed slopes it took to get that level of prediction and how many we could have estimated, degrees of freedom left over. If you take sums of squares, divide it by degrees of freedom, we end up with something called mean square. So we have mean square for the model, mean square for the residual, and we end up with this table. And this is what's on your output. So it's trying to partition the total information that we have in this outcome into what is known versus unknown. And it's trying to judge how good the known part is relative to how many fixed slopes it took to get there. That's the idea. So the model part, the part that's known, is the difference between the y that is predicted by the fixed slopes and the y that's just the sample mean. So remember, if you know nothing else about a person, you predict the mean. So this is trying to see how much better we did by adding my two fixed slopes to differentiate the three groups in this case. It wants to know how many slopes we estimated. So k is the number of fixed effects, minus 1 because we don't count the intercept, because that's always part of the story. And so you end up with this thing. So it's like information per slope estimated. Information that is known relative to estimated slope to get it there. The second row is the leftover part, the unknown. So it's the difference between the actual y and the one that's predicted by the model. How far off are you still? How much information is there yet to be understood by parameters that are yet to be estimated to explain it? So it's your sample size minus the number of fixed effects you've already estimated. That's what's left. Hey, come back. And this one, hang on. I just noticed this. There's another inconsistency. Let me find it. Come back. And minus k. There we go. And that one. MS means mean square. Yep. So the first one is information known relative to slopes estimated to get it. The second one, residual or error, is information unknown relative to things we could still estimate. And the ratio of mean square model to mean square residual gives you a test called F. And F has degrees of freedom for the number of slopes that you had to estimate, numerator, and degrees of freedom denominator for the number that are left. And so F looks like this. Its shape depends on your degrees of freedom, but it looks sort of chi-square-ish. So in our example, the table that shows up on SAS, I have taken and annotated a little bit so we could follow it a little more easily. So information known, SS model is 14,000 and some change. We estimated two slopes, so mean square for the model is 7,000, whatever. Residual information left over, a whole lot of that, a whole lot of degrees of freedom left over, mean square residual. So mean square residual, that's your residual variance. 171 in this case. So the information known over information unknown, after factoring in degrees of freedom for each, that's your F. So 7,000 and some change divided by 171 gets you 42.
Can I know what's the x-axis for the f distribution?
Say that again?
The x-axis for the f distribution, what's the one?
It's the obtained value of F.
Oh. What about the y?
Y is a, let me think. Yeah, it's density in this one. I don't know what their, what this number is, but it should be, it's related to likelihood in this case, since it's a continuous distribution. So you can think of it as tendency, it's like a, not quite probability, but I'd say some sort of measure of likelihood. So this is another thing that shows up on your output, as well as a p-value for whether or not it's significant. Then R square shows up also as SS total minus SS residual over SS total. So let's take a look at that table right there. So we spent 2 slopes to get this much sums of squares model. Sums of squares divided by degrees of freedom is mean square. We still have this much information divided by this many other things we could estimate to track it down. The 125,000 divided by 731 is this mean square. The 7207 divided by 171 is the 42, and it's not 0. The sums of squares total here minus sums of squares residual, make sure that's right, yep, divided by this one is R square right here. So I have bolded the things that would go into your report, in addition to degrees of freedom, and an example of what it would look like right here.
Should we also divide the total?
No, they don't bother with that one. They could, but they don't. Like, they just give you these 2 things as sort of a reference benchmark. But yeah, one could, but it's never done because no one does anything with it, I think. So putting all of this together relative to the information that was in the empty model, we have captured about 10% of it, R square. Is 10% better than 0? That's what F tells us. So the way that you write a description of your F test here, your multivariate walled test for testing more than one slope at a time, is F numerator degrees of freedom, so that's number of fixed slopes in your model, denominator degrees of freedom, how many more slopes you could have estimated but you didn't, equals the F value. It is tradition to give you the mean square error as MSE, or mean square residual. The reason for that is that if you give these 4 numbers, anyone can reconstruct the rest of the table as linear combinations. And then last but not least, the p-value. So that's an effect size that tells us the strength of the relationship between our 3-category nominal predictor and our outcome. The other way you can think of R square, besides just the proportion reduction in error variance or residual variance, is as the square of the correlation between the y that's predicted by the model and the real one. So I'll say that again. R square, as given there, the 10%, that is the square of the correlation between the y hat that's predicted by the model and the real y. So of all the reasons why some people make more money than others, 10% of it is associated with self-reported class. That 10% is significantly greater than 0 according to my F.
Is there a scale for the F?
Nope. The scale for it is just depends on numerator and denominator degrees of freedom. So it's the same idea though of being like out on the tail, but F can't go negative, so all the tail is on the right side. So there's a critical value that's associated with this in which you say, like for this one, like for degrees of freedom, numerator 4, denominator 12, the critical value for F is 3.25, so that 5% is out here. So it's the same principle as T and Z, except it's only on one side. But yeah, you have no idea if 42 is a lot. What, in theory, the lowest that it can be is 1, because it's a ratio of known to unknown, but I've actually seen Fs go under that, meaning you did worse than chance with your predictors. I've done it, not to brag or anything, but yeah. Okay. So yeah, you wouldn't know, like the empty model I think makes it easier to understand where that R square comes from. It's roughly 190 minus 191 divided by 190. It works out to be really close to this R square, but not quite. This one's based on sums of squares. But in models where sums of squares aren't the way it's estimated, R square comes out as a proportion reduction in variance. Same way you would think of it more intuitively.
So can you say that one more? So 10% of the prediction.
10% of the variability in income is accounted for, is explained by, is attributable to the differences between the three classes.
But self-reported.
Self-reported.
Okay. So I'm
Yeah.
just trying to like logistically think how that works. But
So that means 90% is up for grabs.
That's a lot still.
That's a lot still. Yeah. And R square of 0.10 is actually kind of high for social science research, but considering I'm basically predicting income with a categorical version of income, you know, it works out well, right?
Okay.
Yeah, no, this is not this is sort of theoretically bankrupt. That's not my area, right?
Okay.
So it's your job to come up with research questions and variables that make sense, right? It's my job to show you how to put it into SAS. So, all right. Yeah. So standardized effects. This is going to be probably one of the last times you see these because they don't make sense in a lot of situations, and this is one of them. So a standardized slope, when you're talking about a binary variable, these two predictors have to work together to clearly delineate the three groups, and so each one by itself doesn't really make a whole lot of sense. Another way that is more common when you're talking about groups and mean differences is something called D. Have you heard of this, Cohen's D? You have, see? It's coming, it's cool. Let me get to this one. So now you know three effect sizes in terms of their metrics. You know R. R ranges from -1 to +1. There's various kinds of R's, but that letter means that range. Now you know R square, which is R squared, thus ranges from 0 to 1. And here's another one, D. It's a standardized mean difference. So you can calculate this using the original group means and a pooled standard deviation, or you can backwards engineer it from your t-test on your output. And you can compute between D and R as well, and one of the handouts I gave you a few weeks ago has a bunch of conversions like this. But I wrote a little program to do this for you because SAS wouldn't spit it out, and I don't want to do math by myself. So let me show you very briefly here. We'll return to this next time. In the SAS code, there's something new that I added. ODS output. This is a command that takes the tables of numbers and it saves them as SAS data sets. You can then ask it to do math on the SAS data sets rather than getting your calculator out. So to use this, you have to know what SAS calls its tables of output And so I looked it up for this one, and I wanted it to save, this is page 4. I wanted it to save the table of estimates that I requested, these ones right here. So it's saving that. Saving it as a data set where these are the rows and then these are the columns. I then took that data set and asked it to compute another column that is Cohen's d using that formula. 2 times the t value divided by the square root of the denominator degrees of freedom, which was not saved in the table, so I had to input that myself. I then asked it to print that little table as my output, and here it is. So this is exactly the same information up here, except I added one more column to the right, which is Cohen's d. So the way that you interpret Cohen's d is as number of standard deviations different, your group means are. So low versus mid is about 6/10 of a standard deviation. Low versus upper is about 1/3 of a standard deviation, 0.2, 0.27, and low versus mid is 0.05 standard deviations. So these are standardized mean differences. It's more intuitive when you're talking about differences between groups than R. But R and D are related to each other, so you can always get back and forth. And last but not least, words. So you'll get a chance to practice filling in the words at some point. Not yet, but soon. And then closing the file, closing the everything that I did here. All right. So questions before we adjourn?
I wonder why you said the F test tell us R square is.
Because that's what it means. Let me find it. Where did it go? I have it in here somewhere. Where did it go? Yeah, it's, I think that's all I had on that. So you can rearrange, there's another formula that gives you F out of R square right here. So that might make it a little more obvious how they're related. But yeah, you can think of F as a ratio of what you know to what you don't, corrected for how many things you had to estimate to know what you know.
But how we know why it's significant or it's not significant?
Because it's compared to, F is a distribution. So just like T or Z, and you have a critical value under which you know the area that goes to the right. And so if you have an alpha of 0.05, then for instance, you have a critical value that would be here, if these were your degrees of freedom. And so if your obtained F is greater than the critical value, you know that the result that you have is not likely to have happened by chance if there is no relationship in the population.
So here in our example, our significant value, in the example here we have the lower middle.
Mm-hmm.
So F is 42, so the significant value is.
The significance value is given right next to F, right here. It's P less than. Yep, SAS will give it to you. Yep, it's the exact P value. You don't have to worry about looking up the critical tables or anything. Yep. Sure. Others? Okay, then that is it for today. Office hours later. Let me know if you need anything.